Hello everybody, it's for me a great pleasure to introduce you the next speaker of today, who is Tom Sideris from the University of California at Santa Barbara, and the title of the talk is Almost Global Existence of Small Solutions for the 2D Incompressible Hookean Elastodynamics. So, Tom, please.
Okay, thank you, Luis. Okay, I thank Felipe and Hermano for inviting me here and giving me the opportunity to congratulate Gustavo on the opportunity of his 60th birthday. Gustavo has been my good friend and colleague for more than 20 years. Those who know Gustavo admire and appreciate, as I do, his charisma, originality, and tolerance, all wrapped up in a lighthearted sense of humor. Gustavo's charisma is such that whenever he jumps into the swimming pool at his club in Santa Barbara, a group of young women follow closely behind, vainly trying to match his pace. Gustavo's original mind leads him to consider deep problems, such as what would happen when you put a shark and an alligator together in the water. I suspect that, like his great hero Ignatius J. Reilly, Gustavo would prefer to live in a more intellectual period, such as the Middle Ages. After much years of observation, I believe I can infer Gustavo's philosophy of life. It is one of tolerance, which could be summarized by something that he once told me. Do whatever you want, just take a shower afterwards. Okay, I think I just lost a friend, but we'll see about that later. Okay, so I'm going to talk about some joint work with Sen Lei and Yi Zhu from Fudan. Okay, so, excuse me. So we're going to talk about initial value problem for equations of motion that come out of isotropic elastodynamics in 2D. And the main result is one of almost global existence for, let's say, small initial data. And the method of proof, which I'll try to explain, is based on energy estimates, but they have to be combined with decay estimates, since this is a perturbative argument. And I'll try to explain where these decay estimates are coming from, and then show how there's a little twist at the end using something called the ghost energy method. And the argument exploits the structure of the nonlinear terms in a very crucial way. So let me begin. So I'll start out with some preliminaries to try to explain what the problem is here, and then leading up to statement of the main result. And then I'll try to outline the proof, giving you the general setup, and then just a summary of the estimates strategy, and then the linear estimates, and so forth. Okay, so let's begin with just describing the basic kinematic quantities that we're concerned with in elastodynamics. And the basic quantity is the motion, which is a one-parameter family of deformations. So we're looking for a map which takes material points, capital X, to their position, little x, at time t. All right, and this is what we would call a material field or Lagrangian field, because it's a function of the Lagrangian variables capital X. Connected to this is what is called the reference map, or also sometimes called the back to labels map, which is just the inverse mapping. So it takes you from a spatial location, little x at time t, to the original material point, capital X. And this is a spatial field, because it's expressed in the spatial variables or the Eulerian variable. Okay, the deformation gradient is just the gradient with respect to capital X of the motion. But we're expressing that using the in spatial coordinates using the reference map. And the final quantity that we'll be using is the velocity vector, and this is just the time derivative of the motion. But again, we'll express that in spatial coordinates using the reference map. So these two guys are spatial fields. All right, now there's some natural consistency equations that follow from all of this, because the deformation gradient and the velocity are both derivatives of the motion. And this basically just expresses the relationship between the spatial derivatives and the material derivatives. And these relations just come by the chain rule. Now, of course, if we consider the fact that the material derivatives commute with one another, we can express that in terms of the spatial coordinates. And that leads to a couple of equations here. All right, so the first equation here, to call it transport equation, is simply expressing the fact that material space and time derivatives commute. Okay, if you express that statement in spatial coordinates, then you'll get this nonlinear transport equation. So that will be one of our equations. Also, we can express the commutativity of the material derivatives with respect to the space variables. Again, if we convert that to spatial derivatives, then we get this family of constraints here. All right. So we're going to be working in spatial coordinates, and it would be a fair question to ask why do that if these things become more complicated. And I'll explain later the reason why we find spatial coordinates to be more convenient. All right, so this is a result about incompressible motion, which basically means that the deformations that we're trying to construct should be volume preserving. All right, so for each time, this diffeomorphism preserves volumes. And this implies a couple of things about the velocity. First of all, it must be divergence-free, and the deformation gradient then must have determinant 1 everywhere, okay, which is equivalent to this condition. All right, so if we start with an incompressible motion and define the deformation gradient and velocity as I've done, then these conditions come out. Now we're going to be looking at the equations written in terms of the velocity and the deformation gradient. So the next point I'd like to make is just the converse. So if we are able to construct a velocity and deformation gradient which satisfies all of those equations that we just saw, and if initially the field F is the gradient of an incompressible initial deformation, then we can recover an incompressible motion by basically by finding the flow of the velocity field that we have. All right, so if we have the velocity field and deformation gradient which satisfies these conditions, then we can recover an incompressible flow or incompressible motion by finding the flow of this velocity field. So therefore, we'll be looking at the equations for F and V. Now, what we have so far is incomplete. We still need the equation of motion, which captures the physics of the problem. And the best way to write down the equations is to use the principle of stationary action applied to a Lagrangian. The Lagrangian in elastodynamics, or actually in elastostatics, depends on an object which is called the strain energy. And this is a function of, in this case, 2 by 2 symmetric matrices into R. 2 by 2 because we're looking at the two-dimensional case. And basically, it depends on this symmetric expression in the deformation gradient F. All right, and allowable motions should be formal critical points of this Lagrangian. All right, but we're looking at the incompressible case. So, excuse me. So this optimization problem is subject to a constraint, right? This is the constraint of incompressibility. So what we want to do is find the equations of motion, extreme points or critical points of this Lagrangian subject to this constraint. So for simplicity, we're going to consider the so-called Hookean case, which is basically the simplest possible strain energy function that you can write down, namely the gradient, deformation gradient squared. Okay, so we can write it as 1/2 the trace of F transpose F. So this is consistent with our definition here. Now, if you well, just a remark, if we did not have the constraint, the incompressibility constraint, then you probably recognize then that this would just be the Lagrangian for the ordinary wave equation. So basically what we're looking at here is the constrained wave equation in the material coordinates. All right, with the constraint, here's the corresponding Euler-Lagrange equation. So this is basically expresses conservation of momentum. The pressure term here, the P, arises as a Lagrange multiplier, just as you would see in fluid dynamics. Okay, so if you can perhaps recognize the similarity with the Euler equations. And the reason why we've chosen to use the spatial or Eulerian coordinates here is the form of the pressure is nice. This is a nice gradient term. So that's the trade-off. If we use material coordinates, then this would be a more complicated looking nonlinear term. Okay. So here now, to summarize, we've got some PDEs, which are basically these behave like a symmetric hyperbolic system, although it's not entirely accurate because this is pressure term, together with constraints, which express the consistency conditions and the incompressibility that we're assuming. All right, and then the initial value problem is completed by giving ourselves some initial conditions which have to be consistent with an initial incompressible deformation. All right, so now here's our main result. So we're going to be considering solutions, or looking for solutions which are close to the identity deformation. So therefore, F will be close to the identity here. So it'll be a small perturbation G of the identity. So we're going to be writing the equations in terms of those variables, V and G, and looking for small solutions. Okay, so here's what they look like. Here are the PDEs. This is the conservation of momentum equation, and this is our transport equation, just replacing F by identity plus G. And then grouping the nonlinear terms on the right. Okay, then the constraint equations look like this. The incompressibility conditions are here, and then this is the other consistency condition, which again group the linear terms on the left and the nonlinear terms on the right. So we'll call these nonlinear expressions F, G, and H. And notice that the pressure is also over here. We're thinking of it as a nonlinear term because if you take the divergence of this equation here and use the constraints, this linear part will go away. So therefore, the P satisfies this Poisson equation. And so we can think of P as a nonlinear term, but non-local, because when one inverts the Laplacian, of course, that's a non-local operation. All right, so our result is almost, says we have almost global existence. What is that? Well, if we start with initial data, which is sufficiently small, and an energy norm, which I'll make more precise in a little bit, then you have the initial value problem has a unique finite energy solution, which is defined on a time interval, t, where t is rather large, so larger than the exponential of 1 over a constant times epsilon. So although the solution is not global, we say almost global, since this is growing extremely fast as epsilon becomes small. All right, and the solution remains small on this, this time interval. Okay. So again, this is what we mean by almost global existence, when the lifespan of the solutions has a lower bound of this type. All right, so the result actually holds for general isotropic materials, not just the Hookean ones, but I won't define what isotropic is right now. And finally, in 3D, the result is actually, a previous result shows that there's global existence for this problem in the isotropic case. This is a result of mine with Rebecca Thomas a few years ago. So let me explain the difference between 2 and 3D. And as you probably can guess, the difference comes down to the difference of rates of decay of the linear problem. In 2 and 3D, this decay rate for the sup norm of the solution depends on the dimension, and as the dimension increases, the decay rate becomes better. So in 3D, you have a decay rate of t to the minus 1, whereas in 2D, you only have t to the minus 1/2. So that's the key difference, and which makes 2D actually more difficult, and explains why our result is not quite as strong. All right, both the 2 and the 3D results exploit the structure, the so-called null structure of the nonlinearities. Now, if we had a generic nonlinear wave equation without this null structure, then the lifespan of solution would be as follows. In 3D, you would have almost global existence, and in 2D, you would have a lifespan which is proportional to epsilon to the minus 2 power. So it's the null structure which allows us to close the gap here in 2D between this sort of generic decay rate and the decay rate associated with almost global existence. So it's a gap that we need some new ingredients, in fact, to close. Okay, so let's see, in the remaining time, I'll try to outline the proof here. So the first thing is what spaces we're going to be using. All right, so we need to introduce the so-called Kleinerman vector fields, which in 2D look like this. So we have, of course, ordinary partial derivatives with respect to time and the spatial variables x1 and x2. But in addition, we have two other differential operators that we're going to be using here. Omega, which is the rotational derivative, which is here written in explicitly. And this really amounts to, if we were to switch to polar coordinates, this simply amounts to derivative in the angular direction. And also the so-called scaling operator, which is written here, and this is just derivative along rays emanating from the origin. All right, and then the energy that we'll be using will be L2-based energy with all of these derivatives. Okay, so energy of order k of a solution pair Vg will involve the L2 norm of the solution and its derivatives up to some order k with respect to any of these operators gamma here. Okay, so we're not only going to control the standard derivatives, but also the derivatives with respect to omega and s. All right, so for those of you who may not be so familiar with this approach, and let me just give you a few reasons about why we use these vector fields. So the first point that important point is that these vector fields have nice commutation properties. They behave basically the same as the ordinary derivatives. And this means that we can differentiate the equations with respect to s and omega in the same way that we do with the regular derivatives. And this is a consequence of the invariance of the equation under rotations and changes of scale. And here I just mentioned that the actual omega that we actually use is a vectorial version. I just to make things a little bit simpler, I wrote the scalar version here, but there's actually a correction term which is important to include in order to have the commutation properties, but we won't go into that. The second point is that it's very easy, since we're going to be doing a perturbation argument, we need to have good estimates for a linear problem, and it's very easy to get those decay estimates for the linearized problem without any special analysis of the fundamental solution for the linearized operator. So these vector fields make the linear analysis very, very easy. The third point is that at least for large values of r being the length of x, we can replace spatial derivatives by radial ones, because as soon as we can control the omega derivatives, we see that this error term is order 1 over r squared. So for large r, we can use radial derivatives as an approximation for spatial derivatives. So that's very, very convenient. Okay, so here I've made that a little bit more precise. Okay, so we can approximate the gradient of a function by this quantity with an error of 1 over r as soon as we can control the omega derivatives of f. And we're going to do that because that's part of the energy. All right, and a final advantage here is that you get an improvement to the Sobolev inequalities when you include these omega derivatives here. So ordinarily, in 2 dimensions, you have that the L infinity norm would be controlled by the HS norm for s greater than 1, so in particular for H2. But here, if we include derivatives up to order 2 using also the omega derivatives, then we can pick up this decay right here. So you may be familiar with the inequality of this type for radial functions, and this is just the appropriate generalization for non-radial functions. Okay, so again, all of this will depend on being able to control the omega derivatives. All right, so what's the overall strategy of the proof? Well, it's based on the energy method. And so we're going to establish an inequality for the energy. for sufficiently high number of derivatives, and again for small solutions, so we're going to be working with small energy solutions. So this is the target estimate that we're going to establish. And you see here the decay rate is, in red here, is basically t to the minus 1. And the point is that this is better than what you would generically find in 2D. In 2D, what you could normally expect here is only t to the minus 1/2, the decay rate of the linear problem. However, the improvement is going to come from the structure of the nonlinear terms in our equation. So we have a very special a form for those nonlinear terms, which leads to this improvement here. All right, well, given this inequality, then we can easily integrate and find a bound for the energy of this type, and which will imply that the energy remains small, let's say twice the initial energy, provided this thing remains, say, less than 1/2. And that's equivalent to this kind of a bound. So as long as we're less than, time remains smaller than this number, we'll have solutions with energy, energy remaining small. All right, and so this is where the almost global existence is coming from. All right, and as I've said, this improvement here requires careful assessment of the nonlinear interactions. All right, so let me now try to explain briefly where the estimates for the linearized equation come from. All right, so here are our linearized PDEs. Okay, so this is the conservation of momentum, this is the transport equation, and these were the equations coming from the constraints. All right, so now we'll do the following. First of all, we're going to use the scaling operator, and which will allow us, the scaling operator was just TDT plus RDR. So we can rewrite that and replace, multiply these equations by T and replace TDT by S minus RDR. Okay, so we'll do that in both of these equations. And likewise, in the second group of equations, we're going to replace the spatial derivatives there by radial derivatives using our decomposition that I mentioned before. Okay? And then rearrange the terms. So if you do that, it's just a, elementary algebra, you'll get a bunch of equations that look like this. Okay, so this is very, very straightforward. Now the expression, the operator here in red is important. So basically, that operator, given our constraints, is an elliptic, turns out to be an elliptic operator, when, at least when r is small, so less than half t. And the ellipticity constant is proportional to t. So as I'll try to explain, this leads to what I would call local energy decay. So that's the first consequence of these identities. And the second consequence is that we're also going to get decay in L2 for certain special quantities, certain special derivatives. Now, in general, energy should be conserved and will not decay. Of course, we see that even at the linear level. So therefore, not all derivatives will decay, but what we'll see are there's some special components of the solution that decay in L2, and which tells us where the energy eventually accumulates. And those will be the terms that we then have to focus on. All right, so first of all, let me explain very briefly about the local energy decay. I'm going to oversimplify this a bit. All right, so the ellipticity estimate tells us that we can control the gradient of the solution by the what I claim was an elliptic operator in this region. And this t here is coming from the ellipticity constant. So then if we use the equations, we can replace this by the stuff on the right-hand side. Then those nonlinear terms can be interpolated and to lead to an estimate of this type. Now I put the little wiggly line under the interpolation because really in order for this to be true, you can't do it just at the level of first derivatives. You have to do you have to include higher derivatives up to a certain level. But morally, this is the kind of inequality that will come out. Now, if the energy is small, then we can bootstrap this and conclude that this weighted energy here is controlled by this weighted L2 norm is controlled by the energy. And so that will tell us that the energy inside this region here actually decays like t to the minus 1, provided we can control the standard energy. All right, so that's the decay of local energy. All right, so that means the main contribution will occur outside the region in the region r greater than t over 2. All right, the other thing, application of these identities is the decay of in L2 of certain special derivatives. All right, so if you go back to those equations that I had a few slides ago and you manipulate them a bit further, you'll find a pointwise estimate like this. So you see here are a couple of what I would call special derivatives that have these good estimates. So you notice these weights. That's the important point. Here L stands for linear. This is linear stuff. So this is derivatives up to order 1. And N here is just the nonlinear terms with the weights here. Okay. So again, this is pointwise. So and it's just an algebraic manipulation, nothing more. Well, if we take L2, then of course we immediately will get an estimate like that. And then an interpolation argument similar to the one I mentioned a minute ago allows us to control these nonlinear terms using the local energy decay. We can control all of these simply by the energy. Of course, the linear terms are, by definition of energy, are controlled by this and by interpolation, and is also controlled by this using the local energy decay that we've established. Okay. Now, that's a very brief summary of what goes on. But the analysis in 2D is at this stage is actually a little trickier than in 3D because you're also using the structure of the nonlinear terms here to complete this interpolation argument. The Sobolev inequality alone is not enough to absorb the t to the first power, r to the first power here. It's really the structure of these nonlinear terms is being used already at this stage. Okay, as I hinted before, the local energy decay basically makes our life very easy in the region of small r. So when we do energy estimates, then that case is rather easily treated. Now, one of the defects of this approach is that if you notice that we really only have these estimates for derivatives. So in the local energy decay, you see there was a gradient here, and also these special quantities which we've shown to decay in L2 have derivatives here. And of course, then by taking higher derivatives, we can include any of the gammas here. But the point is that we always have to have one ordinary derivative out front here in order to have this type of estimate. So that will come back to bother us a little bit later on. Okay, And just a remark here, these linear estimates are really an implementation of a more general result for certain types of symmetric hyperbolic systems, which is a result that I had back in 2006 with Becca Thomas's. All right, so now let me talk about the structure of the nonlinear terms and how they work in the energy estimates. All right, so just to illustrate, I'm going to take one of the terms that occur in the equation. This is the G term, which came from the transport equation. Well, the other terms are similar, so this is enough to get the flavor. All right, so we're going to use the fact that because of the local energy decay, we only need to focus on large r greater than t over 2, let's say. And so we can use our approximation of the gradient by radial derivatives in that region with an error which is of higher order. Okay, so if we do that, here's what happens. So here's the nonlinearity G, and then if I replace the gradient here by radial derivatives, I get something which can be approximated. This is the first order approximation here with the radial derivatives. Omega is just the unit vector in the direction of x. All right, so I didn't put the argument, but this is, these functions all depend on x. So this is a pointwise decomposition here. And then just simply rewrite this in the following way. And we can regard this expression as a certain bilinear form in the pair Vg and dr of V and G. Okay, and here is the bilinear form that I'm talking about. All right, so this is the main piece of the G nonlinearity after we make this replacement. Okay, now we're going to decompose the solution, Vg, into the good pieces and the bad pieces, all right, in the following way. All right, so G, we'll think of it this way. So G, of course, is a matrix. I can write it as G times the identity matrix, and an identity matrix can be written this way, all right, in 2 dimensions. All right, so given that, here's a very simple decomposition. So we can write the pair Vg as the sum of these 3 guys. So if you go backwards, just add these together and they add to Vg. Why are we doing this? Well, you notice that here and here are the good quantities that we saw before. Okay? So we can write decompose the solution of this way. So the sum of 3 components, 2 of which are good. Good means they decay in L2. And then this term here, which will end up being the main, carry all of the information of the solution. All right. All right, so as I said, the previous estimates for the special quantities tell us that these 2 components decay in L2 at a rate of t to the minus 1. So this is going to be the key. This is where all the information is carried. All right, so now we take our nonlinearity here. Well, we go back. We have the nonlinearity, which is expressed in this bilinear form. And now what we're going to do is decompose Vg in the sum of those 3 components. So there'll be, at first, it would seem 9 terms if we expand this out. However, oops, I'm sorry, I'm in the wrong direction. Oops, sorry. Okay, so here it is. So we replace the pair Vg by the decomposition, and there's a bunch of cancellations. So with this bilinear form, if you have either j equal 1 or minus 1, the self-interaction of pi 1 with itself and pi minus 1 cancels. Also, the interaction of pi 0 with either pi 1 or pi minus 1 is 0, and in the opposite direction as well. So we're left with only 3 terms from this interaction. And you notice that here we have good terms, right? The good terms being pi 1 and pi 0. In particular, here, these are good because it's not only the good component, but with the derivative. And so those are the things that decay in L2. This one, although pi 1 should be good, it's not immediately clear how to deal with this term because there's no first derivative here. So you remember our estimates give us something for this component when there's the radial space derivative there, which we don't have. So this is the final point. Anyway, to summarize this, discussion here, there's no self-interaction of the bad terms pi minus 1. So pi minus 1 will occur only here, linearly. All right, so that's the key to the null structure in this equation, in this system. No self-interaction of these bad terms. All right, so what about the remaining terms, the one that I had in red there? All right, so for this, we're going to use an idea of Alignac, which is called the ghost energy method. And so this is how we treat this remaining term, the one with no space derivative. All right, so in the energy method, we're going to include what we call a ghost weight. The ghost weight has this form. It's the exponential of a kind of traveling wave, if you like, q. A q is, well, this is basically the arctangent function. It's a nice bounded function. And so this weight here is going to behave essentially like a constant. All right, so for that reason, we can think of it as a ghost. All right. All right, so as I said, this exponential here is essentially a constant bounded to below and above and below by positive constants, since this q is bounded. And if you include this in the energy method, then it gives you control of this space-time integral here. And what you notice is here are those special quantities appearing again, but without the space derivative. All right? So we don't have the L2 decay that we had before, but we have this space-time decay with this extra weight here. And that turns out to be sufficient to handle that last remaining term. All right, so in the last 5 minutes, let me explain in a simpler situation how you end up with this term from the energy method. So instead of the complicated elasticity system that we have, I'll illustrate with the wave equation. And really, this is very much the same for the more general elasticity system. All right, so if we start with the energy, we start with the energy identity for the wave equation, and energy identity says this, where E is the energy density, P is the momentum. And we get this identity, as everyone knows, simply by multiplying the equation by the time derivative of u. All right, now we'll take this identity and multiply by the ghost weight, and if we commute with the derivatives here, we're going to pick up an extra term here. All right, then we'll proceed as usual, integrate with respect to space and time. And here's what happens. You see, this quantity here gives us exactly what correspond to our special quantities. Namely, here you see the derivative along the light cone, and this is the radial angular derivative here. And the q prime gives us this weight of t minus r to the minus 2. Okay, and everything comes with a good sign. All right, so this is positive, the sum of squares. and this has a good sign. And so, so it occurs with a good sign, and therefore we're going to get an estimate for that. All right, so if you do exactly the same thing for elasticity, you'll get the thing that I said with the good quantities. Okay, so thank you.